So today I'm really glad to be here, and I would like to talk to you about a problem at the intersection of queuing system and multi-arm bandits. So this is actually an ongoing work. We have some interesting findings, but we may have raised more questions than answers. So I'm really looking forward to hear your thoughts and comments. Okay, so this is a joint work with the Yifei and Zhiyuan, both from Tsinghua University. Okay, so let's get started. So we look at a queuing system. In this queuing system, we have k servers, and each server has its own queue. Okay, and jobs arrive to the system over time. Whenever a job arrives, we need to assign the job to one of the servers immediately. Okay, and so for example here, maybe we give this job to server 1, and then once it goes there, because there's nothing in front of it, it gets into service immediately. And the service time, the time it takes, follows is modeled as a random variable that follows the exponential distribution with rate mu1. So on average, it takes 1 over mu1 time to finish it. So mu1 is called the service rate because then server 1 serves jobs at rate mu1. Okay, and then similarly for the other servers, they have their own service rates, and we are interested in this setting where the service rates are different. Okay, so this is motivated by like, for example, in today's computing systems, the servers are really heterogeneous. They may come from different times, and they are of like very different configurations, so they have very different service rates. Or like another example I like is like, so because the servers are usually shared by different applications, so the capacity available to this particular application might be varying over time and might be very different on different servers. Okay, so those service rates are different. And then when we design the policy for choosing a job assignment, the goal is to minimize the job delay. So job delay is the time from when the job arrives to the system until it gets completed. Okay, so then you can probably imagine that in this system, if we want the job assignment policy to work well, it will give certain preference to the faster servers. Okay, however, those service rates may not be known upfront. Like again, like from this dynamic example, like where the servers are shared by different applications, so you may not know ahead of time like how fast the servers are. Okay, so then how should we do the job assignment here? Okay, so we so this is basically the question we want to answer here. And what we can do is we can send jobs to different servers, and then we can observe how long does it take for each job to get served. And then like we get random samples of the service time. So in that sense, this problem resembles the multi-armed bandits problem in certain aspects, right? So here, when we send the job to a server, it's like pulling an arm, like if we view each server as an arm, okay? However, I wanted to point out that those two problems are different because like basically our system here, our queuing system, I think there should be, yeah, here. Our queuing system here has states. The queue length are the states of the system. So a particular implication of that is like the actions here, like where you send the new job to, is not exchangeable over time. And this is a simple fact of a queuing system, but I just want to make it super clear. For example, like if we consider 2 servers, and this is the job arrival sequence. If we send like the jobs to server 1 first, and then server 1 and server 2, so our action sequence is 1, 1, 2, 2. And if we compare it to the other case where we send to server 1 and 2 and 2 and 1, we can see that if we do the first thing, the job B here gets queued behind A, so it takes longer to finish. So basically, if we swap the order of the actions, we get different completion time for B and also for D. So the total job delay would be different. Okay, so the action sequence is not exchangeable. And basically this is because we have the queue length here. Okay, so that's why they're different. But when we think about this problem, we can still think about the case where like if the service rates were known, then what should we do? Okay, so for this problem, it helps to think about the arrival rate, because like in multi-armed bandits, if you know the mean reward of different arms, you probably just want to pull the optimal arm, right? But for this problem, we cannot just use the single fastest server, because like this arrival rate is the number of job arrivals per unit of time. If it's higher than mu1, for example, then you will overload the first server. And although it's fast, but there will be a long queue here. So when a new job comes in, it's not fast anymore, right? So, and in general, like even when lambda is smaller than mu1, the optimal policy probably is not to send all the jobs to the fastest server, okay? Okay, so that means like a good policy here should take into account of both the queue length and the service rate. Okay, so for this problem, the optimal policy is unknown. So this, of course, we need to define in what sense it is optimal. Traditionally, usually you look at the job delay in steady state. For that metric, we don't know the optimal policy. For finite time, we don't really know, like, and it's not well studied. Okay, so we don't know the optimal policy, but because this abstraction is very important, many different policies have been proposed, and they either have certain asymptotic optimality guarantee, or they work well empirically. Okay, so in this work, the approach we are going to take is like this. So we're going to pick a good existing policy as our baseline policy. Okay, and then what we are going to do is to mimic this policy. So we want to design an assignment policy, which we call hat, to indicate that we don't know the service rates. And we are going to learn the service rates on the fly. And then like we want to just perform comparably with respect to this baseline policy. And this is in terms of the total job delay. Okay. Okay, so what I'm going to do is I'm going to give you two baseline policies as examples, and then I'm going to generalize a little bit. Okay, so let's start with the first example policy. So this policy is called the join the fastest shortest queue. It's very simple. When the job comes in, you look at all the shortest queues, like the servers with the fewest number of jobs. And you may have multiple ones with the equal number of jobs, and they are all the shortest queues, right? If you encounter this case, then you break the tie favoring faster servers. Okay, so you select the server that is the fastest. Okay, so this policy has asymptotic optimality guarantee for job delay in certain scaling regime. Okay, okay, so this is the policy we're going to mimic, and our regret metric is defined in the following way. So the superscript here, pi hat JFSQ, is going to be the algorithm we are going to use that learns the service rates, and the pi JFSQ is just a JFSQ. Okay, and then this queue length here is the queue length at server I at time t, and we sum them up. That will be the total queue length in the system. And when we do the integral, we have the total delay of jobs that have arrived so far. So the reason that we have an integral instead of a sum is just because we work with the continuous time. It's not super different from discrete time models. Okay, okay. So we want to measure this difference as our regret. And I will come to the related work part later, but this regret notion has been proposed in an existing paper by Sanjay and his co-authors. Okay, okay. So and in particular in this work, we are going to focus on the order of the regret when the time goes to infinity. We're not optimizing, or we're not even explicitly characterizing how it depends on other parameters in the problem. And but I'm sure the dependence is not tight, I think. So that's another that's something I will talk about a little bit later. Okay. Okay. So so when we want to minimize regret, usually we have this trade-off between exploration and exploitation, right? So I'm going to give you an intuitive argument on why exploration is necessary for this problem. But I want you to tell me whether this intuitive argument is correct or not. Okay, so let's think about a very simple example here. We have two servers. The first one is faster than the second one. and the arrival rate is super small. It's 0.01 times the slower service rate. Okay. Okay. So what we are going to do is we are going to do what we call plug-in GFSQ. It's very simple. We just first we estimate the service rates. So basically, in the denominator, this is the mean, the empirical mean of the service times for jobs that have departed from server I. So we take one over that because we want to estimate the service rate. Okay, so we just do this, and then we just perform GFSQ, thinking of like regarding the mu hat as the true value of the mu's. Okay, so we just do this, and then like let's think about the system. Suppose we initialize things like initialize the service rates to be super big. So then for the first two job arrivals, we give them to server 1, server 2. So each of the two servers is going to get one sample of the service time. But after that, like we have this estimation happen to be in this case, mu1 hat, which like mu1 is the fastest server, but mu1 hat is smaller than mu2 hat is even smaller than the true value of mu2. Okay, so suppose we are in this scenario, it happens with certain probability, right? And then like an arriving job usually sees an empty system because our arrival rate is super small. And then like most of the future jobs will be assigned to server 2 because server 2 has a larger estimation here. And if we keep sending jobs to server 2, it's going to improve. It's going to approach the true value of mu2, but it's still above the estimation for mu1. And then like those jobs, we should have given them to server 1 because their delay will be 1 over mu1, which is smaller. And because the number of arrivals is linear in time, so we're going to have a linear regret. Okay. Okay, so that's my argument. Is this correct? Like, has everyone been following? Like what is happening here? What do you think? Is it correct? Like for what it's worth, this was my intuition for quite a long time. Jackie?
It's a probability that like a job will arrive even if there's already one.
Yeah.
And then you'll have to explore.
Right, exactly. So we should have invited you earlier for a collaboration. So this was my intuition for a long time, but then we realized that this simple fact, like once this argument is mostly wrong, although some parts look real. So because like when we give a job to this server 2, although lambda is small, but there's a constant probability that there will be another job that arrives to the system. And in this case, because we are following GFSQ, we're going to give it to server 1, regardless of the values of the estimates, right? So we're going to explore anyway. And then like over time, actually we can show that all the servers get enough number of samples to distinguish their service rates, and we're going to get the order correct. Okay, Sanjay.
It reminds me of the CMU rule pre-exploration.
Yeah, right. I'm going to mention that just in a little bit, right? So yeah, so this is like a kind of a free exploration given by the algorithm, and from here, actually, we can show that. We're going to figure out the order correctly, and we will not suffer from a linear regret. And from here, we can actually prove that we can actually bound the regret of this very simple plugin algorithm. So basically, we can show that at this time point, like suppose the current time is t. So by the way, this proof structure also is very similar to what Sanjay has proposed in his previous paper. So this is current time t, and at time square root of t, the two policies will agree with each other. By that, I mean, if they were given the same realizations of Q length, they would do the same decision, okay? But in reality, at this time point, because a lot of things happen here, so at this time point, their Q length vectors are not exactly the same. But we have another very good property of JFSQ. So we can show that like after this, like those two are basically the same policy. Okay, they are both the GFSQ because they will always agree with each other. And if we can show that they both empty at least once throughout this period with a high probability, then like basically that means they are going to be equal with high probability by time t. So this is basically because we have this so-called monotonicity of the policy. That means if we have two systems both running the same policy, and system A starts with a higher Q length for every Q, then there exists a coupling that maintains this dominance throughout time. Okay, so then like once one of those two systems is zero, is the minimum Q length you can imagine. So it's going to be dominated by the other system. And if the other system also hits zero, then they will be the same. Okay. Okay. And this can be proven using the heating time bounds that come from that can be modified from Lyapunov drift conditions. Okay. Okay. So here, so overall, then putting them together, we actually have a constant regret for this algorithm. Okay, so yeah.
What's little t?
What's little t? That's the current time. We fix the anytime t, and we want to figure out what's the expected difference in the two Q length vectors, and then we will integrate over time.
Oh, but then you are assuming that by square root of t they have agreed.
Right. If t is large enough, we can show that by square root of t they agree with each other with high probability, like some probability like 1 minus 1 over t cubed or something. Okay. Okay. Yeah. So I guess by this point, I think you should be familiar with the setting, so that I'm going to help you like put this result into the literature so we can position this result. Okay, so the high level message is there has been increasing interest in this problem at the intersection of queuing and learning. And a lot of results are for this model, which is a little bit different from our model. So in this model, you have different types of queues, types of jobs, and the jobs are queued at their own queues. Okay, and the servers are here, and each server may have different service rates for different types of queues. And our main reference is this paper I've been mentioning by Sanjay and his co-authors. So there they can show that, like, if you try to learn this so-called simu rule, you can also get a constant regret. And in particular, there's also a phenomenon of free exploration that's super clear when you have only one server here, because then, like, for one server, the server anyway needs to serve all the jobs. And regardless of the order of the service, you're going to serve all the jobs and observe their service times. So you get this free exploration, okay? But the algorithm there did use forced exploration, okay? And then there have been, like, if you were here at the beginning of the program, you may remember this talk given by Amy Ward on another problem. This is similar in this setting, but the jobs in the queue could abandon. And then, like, there, you want to learn the CMU divided by theta rule. Theta is the abandonment rate. And then, like, there, they also use the forced exploration and get different regret bounds. Okay. And then there's also a recent paper that uses max weight policy as the baseline. But there, they found that even making the systems stable is not straightforward. So they used like a discounted version of UCP to actually get a policy that's guaranteed to be stable. Okay, and there are the related models. For the interest time, I'm going to skip. Okay, so for the I guess I'm running out of time, but I'll need to. Oh, there's another work by us before where we try to use the optimal probabilistic routing policy as our baseline, which is a policy that doesn't depend on the queue length at all. Okay, so the rest of the talk is going to be very brief. So there's another baseline policy called the never queue shortest expected delay. And so in this policy, it has two components. One is called the never queue that says if there are empty servers available, you have to go to an empty server. And out of those servers, you go to the fastest one. Okay, and then, like, there's another add-on part to deal with the case where there's no empty queue in the system. In this case, you compute an index value like this, and you pick the one that has the smallest index value. So what this is showing here is basically the expected delay if this new job is going to join this particular queue. Okay, and this one was proposed super early on, and in the paper, like it's just called NQ, but we call it NQSED for clarity. It has certain guarantee. So for this problem, like can we just do the same thing we did for GFSQ? Like, can we just do the plugin version? Like that's a natural question, right? So the NQ part, the number Q part, actually guarantees that we are going to have a lot of samples of service times. So we should be able to estimate the service rates to a good accuracy. Okay. However, does that guarantee that the plugin version can agree with the original version, like very quickly? So there's a little bit of complexity here. So for GFSQ, for all the Qs not on the diagonal, you don't need the estimation to make your decisions. You agree with the original one. For things on the diagonal, you only need to know the order of the service rates, right? For this particular policy, it's a little bit tricky because every decision here depends on this value, which has a service rate in it. Those two dots here are the case where they are truly equal. Okay, so if we use a plugin version, we're going to have a blurry boundary, but that boundary will shrink over time. We are left with a situation like this. But for those two red dots here, it could go either way in the plugin version because your estimation could be like either above it or below it. And this should be a tie in the original system, but in the plugin system you don't see it. Okay, so then like that makes like because of this, the coupling of the two algorithms becomes complicated, and we actually have a simple fix for this. I'm going to go through this really quickly. So basically, the idea is whenever you want to pick the Q according to the index value, you should pick the smallest one, but we are going to give it a little bit of slack. As long as the Q has an index value that falls within this band, we are going to treat it, we are going to take it into the selection set. And within the selection set, we choose the fastest server. Okay, so basically, because if there's a true tie between those two Qs, both Qs will enter this selection set. If there is no tie between them, then they are going to be separated. So we are going to, as time goes by, we are going to be guaranteed that the selection set only has Qs that are truly tied with each other. Okay, so then like again, we have a similar proof. We can show that this has a constant regret, and then like we actually make very little use of the structure of the index value. So we can generalize this to a larger class of policies, as long as the index can make the system satisfy the following two conditions. One is the Lyapunov drift conditions that we need for the heating time, and the other one is monotone. Okay, so once we have those two conditions, actually we can show that like this modified plugged-in version.
This is the exponential Lyapunov function, right? That's when you're saying this. Because we want geometry.
Not necessarily. We just need we just need the drift to be like negative.
Okay.
Yeah. Monotone is this definition. I said if you run two systems following the same policy, if one system starts out with longer queues, it's going to have longer queues all the way through. Okay. Okay, so yeah, so actually we can check some of the other policies in the literature, and they fit into this class of policies. Okay, and I'm going to skip the summary because I think some questions have like I said, many questions have been bothering me. The first one is, it seems that we have shown that you don't need to do like explicit exploration and then you get a constant regret. Okay, so then what is the role of explicit exploration in the queuing and the learning problem? Okay, potentially, like although we get a constant regret, like I said, the dependence on the problem dimension, other dimensions might be very bad, like the number of servers in the system. So potentially we could use like forced exploration or other forms of exploration to speed up the learning process to even like further reduce the dependence on other problem parameters. Okay, so that's one thing I've been thinking. And another thing is, like we said, we can learn this policy with a constant regret without even explicit exploration. Does that mean like those policies are just easy to learn? Like their learnability is high? So how should we quantify the learnability? And if there, how should we quantify that? And is there a trade-off between learnability and the performance? We don't know the optimal policy. Maybe it's really complicated. That's really hard to learn. So how should we get a trade-off between those? Okay. And also, like because of the motivation, we said that, like the system is heterogeneous because of this dynamic environment. Then what if the system is truly dynamic, that the service rates are even varying over time? Then like how should we do this? Like this is especially inspired by the work by Chen here. Yeah, and yeah.
First comment, it assumes your benchmark. So maybe you need exploration just to test stability of the benchmark policy class. Right.
Suppose it's stable.
I see, but I'm saying, suppose, how do you know if it is? Like all of this is true conditioned on the benchmark class stabilizing the system, which.
Yeah, we assume that like in the work, you mean in the future work, or in the work we have assumed the drift conditions, so it is stable.
Right, but I guess
But here,
I'm wondering maybe the role of exploration is to test that. If it's unstable, we would need to explore to check if, like, maybe to ask it as a question, do we know a way of testing stability without doing exploration?
the stability of the learning
Of the benchmark policy,
of the benchmark policy. Do we know whether it's stable
without exploring.
without exploring? Like like by observing the system?
If you were to just assume the stable benchmark policy for which you know the parameters, would you have enough exploration to notice that like the system has changed?
The system has changed.
Like the underlying parameters have changed. No?
Okay. So we should take this off.
Yeah, we should take this offline. And there's another technical question I've been thinking, which is like our technique here really relies on exactly coupling the two systems. But what if they just deviate a little bit? Like we cannot deal with that in our proof right now, but maybe we should be able to kind of like if they deviate only by a little bit, like the tie there, perhaps they should still perform similarly to each other. Okay. Okay, so yeah, so that's the end of my talk. I think I'm using over time. Thank you so much for staying here.
Any other questions? I know we had some discussion.
So like I have things on works on other settings of this load balancing problem. So basically what they did is like they have policies and they treat the policies as black box, and like at each round they use one of the policies and then they can get like the best of both regrets. And like my question is like, can you do the same thing here, and do you think this kind of ideas will help you to solve this setting?
Okay, I see. So you can observe two policies and you're trying to get the better one out of those two, and you don't need to actually figure out like the statistics of the system. Yeah, that's a really good.
Thank you very much. That's all for the workshop. This is the close of it. Thanks all. Teach